Hello, Mr. Long. This is FRQ2, and it's just an elliptical orbit of a comet around the sun. Okay, so part A asks us to explain why angular momentum is conserved about the focal point, and then write down an equation for the conservation of angular momentum. So here we know that change in angular momentum is equal to net torque times your change in t. And in this scenario, since it's an elliptical orbit, your net torque is equal to 0 because we know that net torque is equal to F times perpendicular to R. And then the only force on the comet is Fg from the planet, but then that's not perpendicular to your R, so that means that your net torque is 0. There's no torque. So since net torque is equal to 0, that means your change in angular momentum is 0, so your angular momentum is conserved throughout the whole thing. And then for an equation for the angular momentum between apogee and perigee, we know that angular momentum at perigee is equal to angular momentum at apogee, and we'll break that up to IP omega p is equal to IA omega A. And then we'll treat the comet as a point mass, so it'd be I will turn into mr p squared times, and then we'll break up omega p to v over r, so vp over rp is equal to m, and we'll do the same for the other side, m times ra squared times va over ra. M's will cancel from both sides, and then each side respectively, rp will cancel with rp squared, and ra will cancel with ra squared. So it'll turn into rp times vp is equal to ra times va. Okay, part B. Part B asks us to explain why mechanical energy is conserved, and then write down an equation for conservation of energy between apogee and perigee. So we know that the total energy in this situation is Ke plus U to the gravity. And then breaking that up, it'd be E is equal to 1/2 mv squared minus g m of the sun. Or in this scenario, I would denote big M as the sun and then little m as the comet all over R. And then when the comet is far away, when it's at apogee, we know that V would go down because it's farther away, so that means your Ke will go down. But then because of that, looking at this function, if you're or yeah, and then this function, U would go up, and then if it's close, that means V goes up, and then Ke will go up, and then U will go down. So then it will just balance out each other. And then for an equation for it, we do 1/2 m vp squared minus g big M or ms, and then m all over rp is equal to 1/2 m va squared minus g ms times m all over ra. Okay. Part C. Part C asks us to prove that the tangential speed will equal to the tangential speed at perigee will equal to Vp is equal to 2g ms all over Ra Va minus Va. Okay, so here I'll start off with the equation we found in part A between angular momentum. So we know that Rp Vp is equal to Ra Va. And then here I'll just isolate for Rp. So Rp is equal to Ra Va all over Vp. And here I would look at the the conservation of mechanical energy equation that we found in part B. So 1/2 m vp squared minus g ms m all over rp is equal to 1/2 m va squared minus g ms all over ms times m all over RA. And then here, little m will cancel out in every term. So we're left with 1/2 VP squared minus G ms RP is equal to 1/2 VA squared minus G ms over RA. And then here, I'll replace RP with what we found earlier. So it turns into 1/2 VP squared minus G ms times VP all over RA VA is equal to 1/2 VA squared minus G ms all over RA. And then here, I'm going to move everything with 1/2 to one side and everything with GMS to the other side. So it'd be 1/2 VP squared minus 1/2 VA squared is equal to GMS VP over RA VA minus GMS all over RA. And then here, I'm going to isolate, or I'm going to factor out 1/2 on the left side, and I'm going to factor out GMS to the other side. So it'd be 1/2 times VP squared minus VA squared is equal to GMS times VP all over RA VA minus 1 over RA. And then here, on the left side, I'm going to expand VP squared minus VA squared into 1/2 times VP minus VA times VP plus VA. And then on the right side, in the parentheses, I'm gonna combine everything into one term. So it'd be GMS times VP minus VA all over RA VA. And then here we could see that in the top of the parentheses on the right side, there's VP minus VA, which will cancel out on the left side. So here and here. So we're left with 1/2 VP plus VA is equal to GMS all over RA VA. And here I'll just isolate for VP. So I'll multiply by 2 and minus VA. So VP is equal to 2 GMS all over RA VA minus VA, proving the function it wanted. Right, that was part C. Part D asks us to calculate the comet's tangential speed in meters per second at perigee and apogee. So here I'm going to start with the conservation of angular momentum. Again, so RP VP is equal to RA VA. So I'm going to look for velocity at apogee first. So I'm going to isolate for VP here. So VP is equal to RA VA all over RP. And then once again, I'm going to look at the conservation of my mechanical energy. So it'd be 1/2 mVP squared minus GMS times little m all over RP is equal to 1/2 little m VA squared minus GMS little m all over RA. And then here, little m will cancel in all terms. And then here, I'll also replace VP with what we isolated for earlier in the part. So it'd be 1/2 times RA VA all over RP squared minus GMS for RP is equal to 1/2 VA squared minus GMS all over RA. So here I would distribute the squared into the parentheses, and I'll move everything with VA to one side and everything without it to the other. So it'd be RA squared VA squared all over 2 RP squared minus 1/2 VA squared is equal to GMS RP minus GMS all over RA. And here I'll factor out VA squared from the left side, so VA squared times RA squared all over 2 RP squared minus 1/2 is equal to GMS all over RP minus GMS over RA. And then I would divide the right side with RA squared, or everything in parentheses from the left side, and then square root it to isolate for VA. So VA is equal to radical GM over RP minus GM, or GMS, I should say, GMS, all over RA divided by RA squared over 2 RP squared minus 1/2. All this is in the radical. And then this would equal to, write this all out. So constant is just G, and the mass of the sun is 2 times 10 to the 30 all over RP is 5.1 times 10 to the 10 minus G, and then 2 times 10 to the 30 all over RA, which is 6.1 times 10 to 11 all over, alright, so 6.1 times 10 to the 10 squared all over 2 times 5.1 times 10 to 10 squared minus 1/2, and all this in the radical. And then you get VA to equal 5,809.146 meters per second. And then earlier we found VP, we asked it for VP to be RA VA all over RP, and then we're just going to plug in the values from there. So it's equal to RA, which is 6.1 times 10 to 11 all over 5,809.146 all over 5.1 times 10 to the 10. So we will get 6,900,481.95 meters per second, which makes sense because perigee is closer to the sun, so it should move faster than apogee, which is farther from the sun. Okay, that was part D. Part E asks us to prove that the general form of common tangential speed v around the elliptical orbit is v is equal to radical GMS times 2 over 4 minus 1 over 8. Okay, so here I'll start off with, we know that in elliptical orbit, we know that the total energy can be written as negative G M all over 2A, 2 being the semi-major axis. But we also know that the general form of it is 1/2 mv squared minus G big M times M all over R, and then we'll equal the two to each other. So it'd be 1/2 little m v squared minus G ms little m all over R is equal to negative G ms little r all over 2a. Here I would cancel out little m from all of them, and then you're left with 1/2 v squared minus G big ms all over R is equal to negative G big ms all over 2a. And then here I'll just isolate for v squared. So first I will multiply both sides, or I would move GMS over R to the other side. So 1/2 v squared is equal to GMS over R minus GMS over 2a. And then I will multiply both sides by 2, so it'll be v squared is equal to 2gms all over r minus 2gms over 2a, and then the 2's will cancel out for 2gms over 2a, and then you left with v squared is equal to 2gms over r minus gms over a. Now factor out gms to be v squared is equal to gms times 2 over r minus 1 over a, and then I'll just radical it to isolate for v. So v is equal to gms times 2 over r minus 1 over a. Okay, part F. Part F asks, let me pull it up. Okay, that just disappeared. All right, part F asks that if the comet were in a circular orbit of radius r naught is equal to rp, is its velocity v naught greater than, equal to, or less than the velocity vp of the original elliptical orbit? Okay, so in circular orbit, we know that fc is equal to fg, and then breaking those up will be mv squared all over rp, which is equal to gms times little m all over rp squared, and then little m will cancel out, and then one of the rp's will cancel out with the other rp. So we know that v is equal to radical gms all over rp. And then in elliptical, we in part E we solved for the general form of it, which is v is equal to radical gms all over 2 over r minus 1 over a. And then here, to make it like specifically for the perigee, since we're comparing it from vp of the original elliptical orbit, we just replace r, which is rp. So gms all over 2 minus rp minus 1 over a. And then here, comparing the two, we can see that they both have a radical and a gms. So then here I would just ignore it and just compare the 1 over rp and then the stuff in this parentheses here. So in the circular orbit, we know that it's 1 over rp, and then here we'll compare it to 2 over rp minus 1 over a. And then here, if we just plug in values straight up, it would be 1 all over 5.1 times 10 to the 10. And then here it would be 2 all over 5.1 times 10 to the 10 minus 1 all over 3.305 times 10 to the 11. And then we got A by doing, because we know that A, which is the same at the semi-major axis, is RA plus RP all over 2. And then we just did that to find A. And then here we can see that for when it was an elliptical, your velocity is greater than when it was in a circular. So to answer the question, if the comet were in a circular orbit, its velocity would be less than, because here, if we just look at r here, your distance from the sun would be less than, because you're subtracting it by the semi-major axis, whereas here it's just rp by itself. So yeah, that is FRQ 2.